But I'm gonna.
Well, okay, maybe that's.
No,
I don't mean that.
I know what you mean.
That, but, yeah.
Will?
Grade the test.
I'm too happy to have graded the test.
That's great.
Let's see here. Here is that. And let's see here. Now, once I get this here, I'll begin with a word of prayer. So, dear Father, we thank you for this day, and just pray that you be glorified in what we do. Help us to understand a little bit more about linear algebra together, Lord. In your name I pray, Lord Jesus. Amen. All right, so here is your mission 3. I know your life is incomplete without a mission to work on. So let's see here. They're not stapled, but they're single-sided because I want you guys to write solutions single-sided. So there you go. I know it is a great imposition to some of you, but there it is. All right, so theorem. Suppose we have a linear transformation, T, it goes from V to W. These are both, finite dimensional vector spaces. Over some field F, right? Then the dimension of V is equal to the dimension of the kernel of T plus the dimension of the image of T, right? This is the dimension theorem. Now, I gave you a quick proof sketch of this before using the, coordinate isomorphisms. And we'll talk a lot more about coordinate maps today, but first we need to talk about this. So I'm going to just try to hit this proof here, and then we'll talk about coordinate change the rest of the day. But the question is, how do you prove this? All right, so let me attempt a proof. It's a reasonable temperature in this room. There's hope I can formulate an argument. I was just teaching in the room I was teaching physics in just now. It was like 90 in there. I don't know, it's just stupid. Just horrible. So, all right, so kernel of T, as we know, is a subspace of V, right? Thus, we can form beta equal to, let us say, V1 vk, basis for the kernel. All right? But then, the dimension of V, so we can just extend beta. Let me call this beta sub, I'm going to call this beta sub something. Let's call it beta sub big K maybe for kernel. So we can extend beta sub k to beta, which is equal to, let us say, and I'm going to do something a little bit weird here for the sake of a larger project I have, which is I'm going to put the extension vectors first, all right, and I'm going to call them W. So W1, W2, forget the 2, W1, W n minus K, and then you got your V1, Vk, all right. So here, here the number of vectors in beta is equal to n, which is the dimension of V by assumption, okay? Why can I do this? Well, any subspace has a basis because it's a vector space, and that gives us a linearly independent set, right? And we have a theorem that we can extend any linearly independent set to a basis, right? Okay, great. Let X be an element of V, then X is equal to a sum j equals 1 to n minus k of, let's say, cj, wj, plus a sum. I'll use an L. And I didn't use I yet. I equals 1 to k of, let's say, bi, vi, just to keep things separate. All right, great. Thus calculate t of x. Using linearity, I can pull the sum out. 1 to n minus k of cj t of wj plus the sum I equals 1 to k of bi t of vi, right? So by linearity of t, all right, we have this. But then what? So let me take a step back here. This chair is always in the way. It's so annoying. There we go. Better. So, what can you guys tell me about this?
Well, T of WJ is in, wait, no. T of VI is in the, no, VI is in the kernel.
Mm-hmm.
Which means T of VI is 0.
Very good. So this is 0, right? Therefore, let's say gamma equal to T of Wj such that j equals 1 to n minus k has the span of gamma equal to TV, right? Also known as the image of T, right? Thus, the set of these guys can build any output vector for T, right? It is a spanning set for the image. I'd like to prove it's a basis for the image. What do I need to do?
Show linear independence.
Show linear independence. How do we show linear independence of gamma? Well, let us consider, you know, I have used C and B. Let me use A. So A sub 1 T of W1 plus dot 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 plus A sub, how many do I got? N minus K. T of W n minus K, right? Equal to 0. My goal is to prove that all of those coefficients are 0. What should my next move be? Yeah.
Assume that it's false.
No, absolutely not. You guys have this penchant for trying to do everything by contradiction needlessly so. It's driving me crazy. Next test, I am taking off 30% every time someone does a proof by contradiction that is not necessary. I've had it. No more of this. Yes. Sorry, I didn't mean to react so violently. It's just, oh, yeah. If I had graded the test, that's how I'd feel. But let's see here. T of A1, W1, AN minus K, WN minus K. How about this? So I think that's what you're about to tell. Somebody else is about to tell me that. Were you going to tell me that, Sam? No? You should just said yes. You were thinking, Ellie, right? Yeah. Okay, good. I mean, this is all we have to work with. T is linear, right? And what does this mean about this contraption right here?
T is 0 has to equal 0, so that has to equal 0.
No. We can't say that.
It's in the kernel.
It is in the kernel, right. If we knew T was 1 to 1, I'd be with you. But we don't know that the kernel is 0, so we can't assume that this is 0. What we can say is that this is in the kernel, right? So if I just call this whole thing Pac-Man, right? Let me just label it Pac-Man. So we have Pac-Man is an element of the span of, well, beta sub k. because remember that's the kernel. Now we can talk about your contradiction, right? Because we have, I mean, it depends on how you want to package it, but we have a vector, right? Which is in the span of these, but it's not one of these vectors, right? This is, by construction, all of these are vectors outside of the kernel. When we extend the basis, we can't, the way the extension works is we have to adjoin vectors outside of the kernel. Otherwise, we'd have a linear dependence. So the only way this can be in here is for it to be 0. Otherwise, there's a linear dependence in the basis beta that we've constructed. So this implies that Pac-Man has to equal to 0 by linear independence of beta, which then gives me, a1 equal to 0, an minus k equals to 0, again by linear independence of beta. So I use linear independence once to see that it has to be 0, and then I use it again to get that every coefficient there is 0. Fun lemma. Almost made this a test question, thought about it. Any subset of a linearly independent set is linearly independent. This is like, but I can't even ask it because it's like the proof is too like, it'd be very hard for me to tell the difference between a student who was completely lost and a student who proved it, because it's just so like surface level, this theorem. So therefore these are linearly independent, right? So then the dimension of V is equal to n, which is of course equal to n minus, which is equal to k, what happened over there, plus n minus k, right? But that's the dimension of the kernel plus the dimension of the image. And so there you go. That is a proof of the rank nullity theorem with not so much as a coordinate map in sight. Pure linear algebra basics extension, right? This is the linear algebraic proof of the dimension theorem. And because I played my cards as I did, it also gives us something kind of cool, which is the straightening theorem, right? The straightening theorem. So if we say, okay, so we're going to use beta as is in the theorem, in the proof, all right? And use gamma equal to basically my t of w1, t of w2, t of w n minus k, right? So so there are n minus k things here, right? And then just whatever. Let me use yet another letter, u. u1 u sub m minus n minus k, where m equals the dimension of w. In other words, what I'm saying is extend the basis for the image to a basis for w. Right? So all of the vectors I have extended there, all the u's, they have to be outside the image. And so if we think about the matrix of T with respect to this choice of basis, what's it look like? So we've got, well, we've got T of, oh man. Oh, it's fine. So W1, so we gamma coordinate of that, and then T of W n minus K, gamma coordinate of that, and then we've got T of, in my proof notation, V1 through VK, right? The kernel basis. So V1 like that. Now by construction, the last bunch of columns are all 0, right? Because those are kernel basis. They send, T maps those to 0, right? So these guys are all 0. This is E1 because the first basis element is that, which means that the coordinate vector of the first basis element is the first standard basis. So this is literally E1, E2, dot, 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 En minus k, and then zeros. And then if we rewrite this, what we've got is the n by n minus k identity padded with zeros. And here n minus k is what? This is the rank. It's the rank of T. I usually call that P in like the statement in the notes. This is what I call the straightening theorem, which says that you can choose a basis for a linear transformation on a finite dimensional vector space such that the matrix has the form identity matrix padded with zeros. You can make the formula for the linear transformation just this dumb by making the bases sufficiently complicated. This is only possible, like this is very kind of boring. It's only possible because we're controlling both the basis of the domain and the basis of the codomain separately. As we go on in this course, we're going to consider problems where we manipulate the basis in the domain and the codomain in the same way. Then we can't be so flippant. But we are able to do this here. And so essentially the deal is, once I develop the coordinate change here business next, that if you have two linear transformations, you can make their formula the same formula as long as they have the same rank. Assuming that they have, their input and output vector spaces have the same dimensions given, then given two linear transformations, one from, let's say for a given pair of vector spaces, I've got two different linear transformations from one vector space to another. I can make both of them have the same formula. In other words, they're really the same linear transformation in some sense, provided that they have the same rank. They're really the same linear transformation in that regard. Now that assumes a flexibility that we are allowed to change the basis and the domain and the codomain at the same time, separately rather. So anyway, there you go. So we're going to move on here. I probably spent too much time on that, but I think it's probably for the best. This is an important theorem in the course, and you should see it worked out in its entirety, and now you have. Now in mission 3, as you look at it, one of them, so like this proof I'm erasing right now, it gives you a method of calculation, right? If you want to like find a basis which straightens the transformation out, what you need to do is find a basis for the kernel, put it last, and then extend that to a basis for the rest of the domain, right? And then you find where those things map to. You make those things the start of the basis for the codomain, and then you have to extend that to the rest of whatever's not there. Now the problem of how do you extend a basis? Well, you just kind of have to, I don't really have a good algorithm because we don't know determinate yet. Once I have determinate, and you guys can, you are allowed to use determinate in your homework since it is a 221 thing. So if you find it convenient to use determinate at some point, feel free. So I guess there's an olive branch for you, I guess. But anyway, so let us talk about coordinate change. So I've got a vector space V, right? And on the one hand, I have phi beta. On the other hand, I have phi beta bar. So two different bases. So on the one side, I take a point up here, x, right? And I can get the coordinate vector with respect to the beta basis. Or I can get the coordinate vector with respect to the beta bar basis. How are these related? How are these related? So the way I figure it out, is I just do like this. Do-do-do-do-do-do. So what's this map? The last shall be first. So phi beta bar composed with phi beta inverse. And that should connect these. So, yeah. Now, down here we're talking about Fn, and we're talking about Fn, right? So this is a linear transformation from Fn to Fn, which means that it can be written as a matrix multiplication. So it is logical to say this. X beta bar is equal to the standard matrix of this gadget, whatever it is, times the beta coordinate. And so there you go. This is the change of basis matrix. And so here, my notation, I believe, is P, basically beta goes to beta bar. I think, well, I got to be careful. Beta bar, yeah. I'm going to double check it. Yeah. All right. Now, if your vector space, if V is equal to Fn, then the coordinate map with respect to beta of x was equal to what? We worked this out before, I think. Or if I didn't, I'm sorry. Here's what it is, though. It is the inverse basis matrix of beta times x. To be, you know, just to, I don't know if see, I'm not sure if I did that in here. I know I did in 221, but just in case you don't remember. So basically x is equal to the basis matrix times x, times the coordinate vector of x. So like this would literally be, you know, like x1 v1 plus da 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 plus xn vn if my basis was v1 through vn. So if this is my linear combination of the coordinates of x with respect to the, maybe, I'll put a bar here just to be weird. And just so you're not tempted to think of the x1 through xn as, you know, the Cartesian coordinates, because they're not in this discussion. All right.
Missed one bar.
I did miss a bar, my bad. So my point to you is you can write x as equal to like this, right? So in this particular context, you can discover the, you know, we have x on the one hand, it's equal to the beta bar matrix times the coordinate vectors with respect to the barred matrix. But by the same token, we can say, well, it's the beta matrix times the coordinate vector of x with respect to the beta matrix. And so in the special context of column vectors, we have the really simple relation between coordinate vectors of the following. But this is special to the context of column vectors. So you can identify in this particular context, this right here is my P beta bar. But generally speaking, for an abstract vector space, you have to sort through this mess. All right? And I have an example in the notes where I do that, but just saying. So that's the one thing. This is how coordinates change for a vector. Then the next question, of course, you want to ask is, well, how do coordinates change for a linear transformation? Right? So let's look at that. So I'll do that.
You didn't close your parentheses.
That's true. So suppose we have a vector space V, all right, linear transformation T, And over here, a vector space W, both finite dimensional. Basis beta over here, basis gamma over here, basis beta bar over here, basis gamma bar over here, all right? So you got the phi beta map, you've got the phi beta bar map, you've got the phi gamma bar map, you got the phi gamma map, you got all these coordinate maps, right? So I'm assuming V is like n dimensional, so this is like Fn. This is another copy of Fn. And I'm assuming W is m, so n as in nanu nanu, and over here W is m dimensional, so Fm, m as in mommy. Right? And we defined how to find the matrix of the transformation, right? You guys remember? So to go from here to here, we defined left multiplication by the matrix T beta bar gamma bar. On the other hand, I could also talk about the linear transformation, the matrix of the linear transformation with respect to the other choice of basis, right? The unbarred ones, which I would draw like down here. Whee! So this would be left multiplication by T beta gamma. And you guys have calculated some of these, right? Then the question is, how are these related? So how is left multiplication by T beta bar gamma bar related to this guy? I really should have done it blue. I'm sorry, I failed my color coding. But I'm not writing it again. Okay, fine. But I did it in another color, so it's still annoying. Haha. So let's see here. So what we want to do is we want to take a trip. We want to take a trip that it gets to the same start and the same end, but it goes through the other map, right? So we'll start here, but we're going to do like this. Do-do-do-doot, 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 do-do-do-doot. So the first shall be last. Last thing was phi gamma inverse. The thing before that was, and I got to keep track of the direction here. So it wasn't phi gamma inverse, it was phi gamma. There we go. And then that was composed with phi gamma inverse to get like that. And before that, left thank you. And before that, left multiplication by T beta bar gamma bar. And before that, composition with phi beta bar. And before that, composition with phi beta inverse. Woohoo! But what we're looking at is the composition, right, of linear maps on column vectors if you play your cards right, right? Check it out. So this right here and this right here, those are both mappings from over here. It's a mapping that goes from FM to FM, and this one is a mapping that goes from Fn to Fn. They're linear maps, therefore they have a standard matrix. It is meaningful to in fact write that this is the matrix of, phi gamma composed with phi gamma bar inverse, my bad, the inverse is inside, times the standard matrix of L T beta gamma, which is of course T beta bar gamma bar, right? And then times the standard matrix of, you got yourself a phi beta bar composed with phi beta inverse, like that. And that is all equal to the standard matrix of the left-hand side, which is T beta bar gamma bar. Lo and behold, this is the coordinate change formula. This is how we change coordinates for a linear transformation.
Real quick, it's in the ones that you says LT beta bar beta.
Beta bar, gamma bar?
Gamma bar.
Uh-huh.
And it also is composed with LT beta bar, gamma bar.
Oh, see, I'm taking the standard matrix of this equation.
Oh, okay.
And the standard matrix of a composite is the product of the standard matrices composed. We proved that. And so that's why I'm doing standard matrix of this. Now the standard matrix, the thing is, the standard matrix of left multiplication by A, it's A. This is an identity. I'm using that here, also here. Now, can you guys tell me what this is in terms of my P notation, the P beta bar, P beta gamma bar notation? What's going on here? What's this equal to? I got to keep things straight. So if I have, we should look at this one. So P beta bar composed with phi beta inverse. Do I have that? Phi beta bar composed, oh, this is right here, right? This is my P beta bar, isn't it? If I'm wrong, let me know. Yeah.
Shouldn't the left-hand side of those equations be just beta and gamma without the bars? Because we're going from just the beta to the gamma without bars.
Well, I'm not sure what you're saying.
On the left-hand side of the equations, left, well, it's
You are correct. Where's my error? Here. So here, just these guys, which is what you're telling me, right?
yeah, and then
Thank you. Very helpful. Excellent. That's why I hate teaching online. That never happens online. You make the error and it just sits there forever and ever. Now, you notice that the pattern here is the opposite of that. But here's a fun fact. This is the matrix of phi gamma bar composed with phi gamma inverse. Because when you invert a composition, it sock shoes, right? It goes in inverse order. So in fact, truth be told, what we have is P gamma bar inverse times the coordinate matrix with respect to beta bar gamma bar times P beta bar. You may remember this from 221 in the special case that we use the same basis in the domain and the range. Then this just becomes P inverse matrix P again. It becomes a so-called similarity transformation in that context. But generally, we have a different change of coordinates matrix here and there. And the one from the codomain appears as an inverse in the transformation, and the one from the domain just ends up multiplying. That's the rule. That's what we worked out. Now I have a calculation I can show you, if I'm not out of time, which is debatable. Uh-oh, I seem to have. Yeah. Well, it's harder to push back the other way. Ah. So begins the story of how I got a hernia in linear. All right. So I actually do have a gory calculation that puts this stuff into practice. Now, in your mission 3, I told you guys to use a theorem in the notes. Like, don't ignore that, please. With the theorem, it's easy, and you're allowed to use technology. That one problem. So, like in the notes, I derive a matrix technique to do the straightening theorem for column vectors, and oh, whoa! I still got 10 minutes, dude. I thought we were going to be like 4:05 or something. This feels amazing. I got 10 whole minutes. Wow. It's like Sunday morning. I mean, Christmas. Let's see here. Wait, which is better? I guess that depends on your church, right? Let's see here. What's that? Can be the same day if you're going to a good church. If your church met on Christmas, that's kind of an indicative. There's something to think about there. Let's see here. Okay, so here we are, eventually. So there's the future. Come on, come back, come back. All right. So like this 3.6.1 business, I derive a method to actually calculate the bases which convert to this, like they straighten it. So like, you don't have to do the whole extension thing I was talking about for column vectors. You can follow my example 3.64 to actually straighten it out if you want. Like here, basically, just to summarize, if you want to straighten, if you want to like similarity transform, not similarity, but this is not a similarity transform. When we multiply by different matrices on one side and the other, they're said to be matrix congruent. Something else. Okay, so basically you take the matrix you got, you pad it with a 4x4 identity on that side. You row reduce, it gets you that. This ends up being the P that you want to put on the left, I think, of PAQ. And then you transpose the reduced row echelon form of the matrix, all right? And then pad that with the other size identity. Row reduce that thing, it gives you this. It turns out that this is the Q that you want. And then, let's see here, R transpose, I've forgotten what R is. I'd have to look back into these notes to remember what R was. But anyway, the point here. What's that? Oh, yeah, well, I know, I'm like, why am I defining R like that? Oh, it's because R is what I'm after. Oh, R is the thing I'm after, which is PAQ transpose. And as you can see, if you multiply by PAQ transpose, like I did, it straightens it. So one of the problems, I'm just letting you use this method. And this can be understood in terms of like thinking about elementary matrices and things, but that's kind of not our course. I'm just sharing with you as a point of trivia for the homework. That's it. That's like as far as it goes, okay? The calculational thing that I'd like for you to understand is basically just mimicry of the proof I did at start of class. So like problem 9 on quiz 3, which was inappropriate because this quiz come after the test, not before it, right? Yeah. So there's that. Now, so we just derived this formula here, right? Do 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 do. Scooch out a bit here. So, whoa, what was that? Did you guys hear that? So this is the coordinate change formula for a abstract, well, excuse me, this is not, my bad. What is this? Coordinate change, I need to go back further. We're still not back. This is after what we got to. Sorry, guys. So this is what we just derived, I think. Yeah, this one. So here it is, I believe. Aw, man. Dudes. Huh. Oh, do you guys see why these are both correct? What's the difference? That's right. So this one I've solved for the beta bar, gamma bar over here. On the board, I have derived the far less interesting. Here's the old matrix in terms of the new matrix you're trying to find. Right? If you're starting with beta gamma, you're trying to find the matrix with respect to beta bar gamma bar. This formula is not particularly interesting. This one is, right? But anyway, they're the same formula, just a question of reversing the roles of the bases, right? So, all right. So my point is just that we have this change of coordinates formula, which we can use, and we'll keep coming back to this. Throughout the rest of the course, we'll need change of coordinates. It really is at the base of like a lot of the things we're thinking about. So here's an example. I have a linear transformation from where? From P2 to complexes. So, and my formula is this. So I'm taking, what am I doing? Oh, I guess I'm evaluating at I, right? T of f is f of I. So that gives me c minus a plus ib. All right, great. And I'm going to use the basis x squared x1 just to be weird, apparently. What's wrong with me? Why am I doing that? Maybe that's a typo. Oh, no, that's fine. It's decreasing order. I'm sorry, it just looks weird to me for some reason here. Fine, but that makes the coordinate vector of ax squared plus bx plus c abc. Great. And over here, basis for complex numbers, you know, a plus ib has coordinate vector ab. Yay. And lo and behold, the matrix for t with respect to the beta gamma bases is that. All right, so you guys know this already, I think. I mean, I know for sure once I grade your test. But on the other hand, if I was to use bases, you know, shifted at x minus 2, and oh, just to make things interesting, I flip-flopped I and 1 here just so you can appreciate how the theorem works, right? Well, then if I calculate the beta bar coordinates of this, I get that. And of course, the coordinate, you know, the complex thing flips as well. I don't know, I don't see that here, but anyway, so, oh, so here I actually worked out, this is what happens when you compose phi beta with phi beta bar with phi beta inverse. We end up with this maps to that, which shows me that the matrix of that composition is, you know, 1, 0, 0, 4, 1, 0, and 4, 2, 1, right? But to find the change of coordinate matrices, you have to kind of like find the coordinate maps and compose them and see how it works, you know? And great. So on the other hand, what I do here, I guess I just did it again. But this time, oh, I decided it was easier to, rather than inverting that matrix, I decided it was easier just to compose the maps in the other order and to find the inverse of that matrix. Why am I finding the inverse of that matrix anyway? I don't know. Why did I do that? I did it. Apparently that and that are inverses. You can try. Uh-oh. Let's not look too much at this calculation. Moving along. Nothing to see here. I'm sure if you work out the details, they'll work. That probably doesn't actually matter, though. Well, anyway. So here's the coordinate change for the complex, and then the coordinate change matrix for the... I'm a little bit suspicious, but hopefully... I think I checked my answer, though. So this is the coordinate change relation, and I'm actually working it out, and I get this. And then just to check my answer, I calculate the matrix of t with respect to the barred bases directly. And to do that, I calculate, you know, input. Here's a natural expansion in terms of the shifted basis, right? What happens? You plug in I, you get this. Multiplying it out gives me that. So remember that in the gamma bar basis, I comes first. So that puts this up here, and that puts this down here. So that's the matrix, and that is the matrix. So if I made a mistake on one of the coordinate change matrices up there, I apparently didn't use it. It looked to me like when I multiply those matrices, they're not inverses, which means I've got an error somewhere in here. Or I've just miscalculated right now because I'm an idiot, which is very possible. Anyway, so there is a gory calculation. Oftentimes, guys, we are in the context of column vectors, and there special things happen. See, because the coordinate change matrix, instead of just having to sort through like that abstract calculation I just did, we simply can use the product of the basis matrix inverse and the basis. So like you can build the coordinate change matrices merely from stacking, like, you know, concatenating your matrices, your vectors from your basis, and then inverting them and multiplying them. So like this is the formula in the context of column vectors. It's just you take the new basis, invert it, times the old basis, the matrix with respect to the existing basis gamma beta, beta gamma rather, and then the inverse of the beta matrix times the new basis matrix beta bar. That is how you change coordinates in column vector space. This is most pretty in the context of converting, say, the standard basis to the non-standard basis. So if we're talking about standard basis, that makes the basis matrix for the standard matrix is just the identity matrix. So like this goes away, that's identity, and it just drops down here to gamma bar inverse standard matrix times beta bar. And this is how we can calculate the matrix for a linear transformation of column vectors with respect to a non-standard basis in the domain and the codomain, simply by this, multiplication. But as I've showed you today, it's more complicated. If we're in an abstract vector space, we actually have to sort through the coordinate maps. But if you understand this diagrammatic argument that I gave you, you don't have to memorize anything. You can simply derive it whenever you need to do it. That's what I do. I don't look out in a book. I don't try to have to go in a book and figure out which one's beta, like these stupid p beta bar notations. Like that'll drive you nuts. You look at different books, they have different notations. You don't have to rely on that. I've showed you how to understand it from following diagrams. And so I think that's useful. Anyway, this is most interesting in the case that we were talking about a linear transformation from a vector space, from Fn to itself, right? In that special case, this just becomes the same matrix both sides, and it becomes a similarity transformation. And that's oftentimes what we're looking at later. But anyway, I think that's it for today. So we can turn it off.